Okay, in this question here, we are going to work a problem without taking into account the effect of the pulley. So it is a massless frictionless pulley. The question is asking us use conservation of energy to calculate the speed of the blocks after M2 had dropped a distance h. So what do we have here? Conservation of mechanical energy, which says gravitational potential energy initial plus kinetic energy initial is equal gravitational potential energy final plus kinetic energy final. So in this case, since both masses are going to start at rest, initial kinetic energy is 0. Initial gravitational potential energy, if our mass is going to be dropped a distance h, I mean from bottom here, h, then we can say that we have an initial gravitational potential energy of m2 gh. We don't have to worry about the gravitational potential energy of M1 since M1 is not going to move up or down. So there is no change in GPE for M1. So we can ignore it. So my initial mechanical energy is just M2GH is going to be equal GPE final. GPE for M1 did not change. For M2 it's going to become 0 plus kinetic energy final. But what's the kinetic energy final? Both masses are going to be moving, so it's going to be 1/2 of m1 v squared plus 1/2 of m2 v squared. So v is going to be square root of m2gh times 2, that half there is going to come to the numerator, over m1 plus m2. Now, what if our pulley actually has a mass? What if it's going to affect the outcome? Now again, we are going to write conservation of mechanical energy. So again, GPE, gravitational potential energy initial plus kinetic energy initial, is equal GPE final plus kinetic energy final. See, this equation is not that different from this equation. Same thing. And similarly, we don't have any kinetic energy at the beginning. GPE initial is just m1 gh. GPE final is again 0. The difference is going to be in the kinetic energy final. What will the kinetic energy final be? It's going to be 1/2 of m1 v squared, that's the kinetic energy of m1, plus 1/2 of m2 v squared, that's the kinetic energy of m2, plus the kinetic energy of the pulley, which is plus 1/2 of I omega squared. Now, they're giving us the radius of the pulley. Omega is related to the velocity of the edge, which is the velocity of the string, by omega is equal to V over R. So this is 1/2 of I V squared over R squared. In other words, my V in this case, and I'm skipping steps, is square root of 2 M1GH over M1. For some reason it's erasing what I write. M1 plus M2 plus I over R squared. So I'm going to rewrite the M1 here since it's not letting me keep it there. So it's going to be M2 plus M1 plus I over R squared. Consider this situation here. We have a mass M that is hung by a string that is wrapped around a pulley of radius R, which is attached to a heavy flywheel. The moment of inertia plus flywheel is I. The string does not slip on the pulley. Starting at rest, how long does it take for the mass to follow a distance L? That's the question. Starting from rest, how long does it take for the mass to follow a distance L? Now, in either case, we can use conservation of energy or sum of all torques and then use kinematics. In either case, we need to use kinematics. If we look at the mass, apply Newton's second law of motion, sum of all forces is equal to ma. The forces acting on it are the gravitational force mg and the tension upward. So if I take this direction as positive, mg minus t is equal to ma. That's Newton's second law for the hanging mass. Now, for the flywheel pulley combination, sum of all torques is equal to I alpha. We have only one torque, the torque due to the tension here. Line of action of the tension is here. So the radius of the pulley, remember, note here, it is the radius of the pulley, not the radius of the flywheel. The radius of the pulley is our lever arm. So T times R, and it's rotating in the counterclockwise direction, and it is rotating in the counterclockwise direction, so it is positive, should be equal to I alpha. And remember that A is alpha R. A is the acceleration of the string, so it is R away from the center here, so it is alpha R. So if we combine this equation with this equation, we get this. Just replacing alpha by A over R. And then what we do is solve for T here. T is equal to I A over R squared, and plug it in the first equation here. Let me use a different color. So if we do that, it's going to be mg minus my t is going to be I A over R squared, and that's equal to be ma. So if we solve for A from there, A is actually equal to mg. Okay, so what I'm going to do, I'm going to move this to the other side and then factor out A. So when I move this from to the other side, I have only mg left. So that's what I have. And then I'm going to factor out A. So A is factored out, and whatever the factor is going to be m plus I over R squared. So if I multiply both the numerator and denominator with r squared, I will get this equation. I don't have to multiply both sides by r squared, but I can do it if I want to. Okay, so now we have the acceleration. To find t, we just use kinematics for this mass. So the displacement equation, y is equal to y0 plus v naught t plus 1/2 of at squared. In our case, our displacement, y minus y0 is L. We don't have an initial velocity since it starts from rest. So my expression becomes 1/2 of at squared. So solving for t, 2L over square root of a, and using the expression of the acceleration from the previous part from here. That solves our problem. Okay, in this situation here, we have an object that's going to roll down an incline. That's making an angle theta with the horizontal. The question is, find the static friction force that causes the body to roll down the incline. Okay, how do we solve this? We first consider the free body diagram of the object. We have Fg plus the friction force plus the normal force is equal to m a center of mass. Our free body diagram, just any way to make sure we remember. Okay, so this is my x-axis. This is my y-axis. Gravitational force is straight down. That's my Fg. Normal force is perpendicular to the incline, so it's going to be this way. And the friction force is going to be this way. Now, along the x, if this is theta, this is theta, we are going to have mg sine of theta, that's the component of Fg, minus F is equal to m times a center of mass. The normal force is not going to have any component. Okay, now we have that. What about the torque equation? The gravitational force is not going to have any torque because the line of action goes through the center of mass. Now, the normal force, same situation. Its line of action goes through the center of mass, so it's not going to have any torque. So the only torque left is the torque due to the friction force. And look at the torque due to the friction force. It is rotating our object in the counterclockwise direction. So torque due to the friction force is F times R. And remember that A and alpha are related through that expression. So we rewrite the torque equation here. R times F is equal to I alpha, I A over R. And then solving for F here, that becomes IA over R squared. Now with this equation and this equation here, A center of mass is the same as A here. This F is the same as this F, sorry about the different notations. So with these two equations, we have two equations with two unknowns. If I'm trying to find F, I solve for A here, which is FR squared over I replace it here and isolate the F. If I'm solving for A instead, I replace the F by its value here. Either way it would work.